far as the course materials in this particular class, that's going to be drawing from these 3 textbooks. So just for your reference, and I'll have them in the notes about what these textbooks are. But actually, this one, there's a PDF of this on Canvas, Introduction to Statistical Learning, SLR, pretty well-known book. We'll have a couple lectures on causality, which is from this, this textbook, which is also available online, and I'll give a link for that. And the last one, we're just going to have one lecture from a time series, which is from this textbook. So if you want reference materials, it's here and available. Most of it is, like I said, available online. Okay. Before I jump into material, just wanted to check if there were any questions or anything from any of the previous lectures. Happy to do just a quick little refresher. And if not, we can jump right into it. Okay. So I will share screen. Let's see if this works. Okay, great. So we will start off lecture 3. Lecture 3 notes. I will say my handwriting is worse on the iPad, so I have to deal with that. So basically, what are we talking about in this course? Regression. So this is modeling the relationship between variables. And I would say about 90% of the class, 95% of the class, we're going to be talking about essentially this, okay? So this is, you got a data set from something in a research topic that you're interested in, and what the heck do you do with it, okay? So.
Can I ask a silly question?
Yeah, no silly questions.
Okay, I've really struggled with the word regression.
Yes.
Do you know the etymology of it, or like what's regressing, or like?
Yeah. I don't know if I actually know the etymology of the word, but when we say we regress like y on x, that means that we want to understand the relationship between these 2 variables. We're primarily in what ways like x leads to something like y, or how it's correlated to something like y. Don't worry about the strict definition. I think we'll kind of see. We're going to build up slowly our intuition about kind of what constitutes a regression, and so hopefully in a couple lectures, if it's still confusing, we can get to it more. I will look that up though, etymology of the word. I actually don't know. Okay, so moving on. Actually, I'm going to make this a little bit bigger. So we are going to draw some data points here. Something maybe like this. Okay. And so we have 2 axes, one with x's, one with y's, right? So you might imagine maybe I have a data table here, x, y, and it's got a couple values, and this has a couple values, and all I've done is I've plotted those dots onto this graph. Okay, now I would like a couple volunteers. Okay, one. Who else? 2, 3. All right, come up here. Come on up. You, sir, have the pen, and I would like you to go ahead and give me the best fit line.
Can I use red?
Yes, you can. Well, we're going to use different colors. Yeah, give me your best shot. Great. We got one line over here. Up next. You can do whatever line you want. All right. Looking good, looking good. Show me, you get blue. Best line. Okay. Slightly different slope. Okay. A lot of pressure, I know. Okay. Great. And for kits, I'm gonna add a best fit line of my own, okay? And we're gonna go like that. Cool, all right. So we're gonna vote for which line you think is the best line. The line that best fits these points, okay? So who votes for red? We got a couple people, okay. Blue? Couple more for blue. Yellow? Okay. Green? No one for green? Okay, who votes for my black line? Yes, all right, thank you. I got your support. Great. Okay. So anyone who raised their hand for the red line? Anyone who raised your hand for the red line? Yes, okay. So tell me what it is about the red line that is drawing it to you.
It roughly follows the entire pattern, it's kind of in the middle all the points.
Yeah. Okay. Okay. Roughly in the pattern, somewhere kind of in the middle of the points. So, are you saying that like if it were farther from the points that we would maybe like it less?
I mostly am saying that like I feel like the rest of them all trend like towards the higher values, and so I felt like that was more just kind of
Okay.
in the average middle of everything. If that makes sense.
Okay. But like the kind of like rough intuition that you're giving, right, is that like there's something about how close the line is to certain points that's like leading you to that, right?
Yeah.
Okay. And in fact, that is, if you think about it, that is an objective measure of how good a fit can be, right? If we look at all of these things, maybe we're all kind of internally calculating, right? Okay, how kind of far away is a line from any of these points? And so if I were to do that with the red line, for example, I could actually like measure that, right? I could take the distance of any point, any one point, and measure how far it actually is away from the red line. And I could do the same thing for all of these guys. Wrong color, hang on. So if I switch to green, I can see how far away each of these points are from the green line, right? Okay, and finding a line that kind of minimizes the distance to each of the points is one of the ways that we think about trying to get a fit relationship, right? That describes the relationship between x's and y's. So who likes that methodology for thinking about the closeness of the fit? Does anyone not like it? Does anyone think that's a bad way of measuring fit? Nobody? Okay. So in that case, let me draw a line that will be better than all of these other lines. Okay, so here we go. Okay. So this purple line that I just drew has no error, right? Because I actually have an exact fit to each of the points, right? So my line will actually traverse through all of these points. So that is something kind of important to think about. And so who thinks the purple line is the best fit line to describe the relationship between x's and y's? Anybody? Yes, you do. Okay. And so, and the basis of the reasoning is because of that, because the points fall exactly on the line. But suppose that these points were kind of derived from some kind of function, some kind of, let's say, random generator, like I'm pulling numbers out of a hat, right? And so if I continue to pull numbers out of a hat, maybe the next set of points might look something like over here, and over here, and over here, and suddenly, right, maybe this purple line has like a massive error, right? Maybe it no longer does a very good job. So we tend to call this over prediction because you are calibrating too closely to the points that are in your data in such a way that you might be missing points that would be described by a slightly sort of different relationship, like the red line or the blue line or something like that. So in this class, this is kind of the balance that we're going to try and get, right? Is this black line that I drew at the beginning, which most people didn't think was very good, except you, thank you, versus this purple line, which maybe we might argue is overfit. How do we get to the sweet spot between those? That might be this red line or the blue line or the yellow or the green line, right? And so there is certain decision-making processes that we have to decide, what constitutes a good line and what is like the form of the line, right? So one of the volunteers, when they came up and they asked, oh, does it have to be a straight line, right? We are going to build up to that. But the straight lines are kind of the easiest to start with, and so that's what we are going to build our intuition up from. Okay, any questions about this whole process?
So with, as you said, over prediction, how do I say? I'm not sure the methods that would give us a line such as the purple line. I'm aware of the linear regression models and such, but
yeah, we're actually going to get to some. We will cover specific methods that will give lots of flexibility in the way that lines will cover these points essentially. And some of them are so flexible that they'll do exactly this and get to zero error. And so we will figure out ways in which we're balancing between this purple line and maybe something like the yellow, green, or blue lines, right? And in fact, if you think about it, there are many different lines that can do what this purple line is doing, right? So I could do something like this, right? And technically, this would this would get to the same sort of goodness of fit if we're just concerned about model error. And so, we're going to look at ways to avoid something like this. Okay. Don't worry, not all of your notes are going to be this messy. So, let me back out here and kind of just reiterate, we're going to be starting with a straight line. Okay, and so as we think about drawing a best fit line through these points, and maybe that looks something like this. Unlike with some of the other lines before, we don't necessarily have to worry about the flexibility in the form or anything, right? We can just simplify, and we can very objectively say something like, if I measure the distances of each of these points to the line, this is an objective measure of the best linear fit. And that is to minimize the distance. Okay, so folks, who's taken some kind of regression class before? Who's familiar with OLS? Yeah, okay. A good chunk of the class. Okay, and so OLS is ordinary least squares regression, so OLS regression. And how does this work? Instead of minimizing this, or let's say, I'm not gonna say instead of. So the way it works is it minimizes the square, the sum of the squared distances between your points and your line. So can anyone tell me why would we square it? Yes.
So then there's no negatives?
Yeah, exactly, right? So if you just took this point, and this was a distance of 1, and this was a distance of 1, it would be, 3, the distance might be positive 1 and then negative 1, and then you add them up and it's 0, and it looks like the error is 0, but actually it's not, right? And so, we square it so that you get symmetrical errors on both sides of the line. Does anyone know why we square it and not take the absolute value? So you actually could take the absolute value, and that actually can lead to slightly different answers, right? Because if you think about points that are far away, when you're squaring that distance, it penalizes it more. So it'll get you closer, or the line will kind of be preferential towards points that are slightly farther away. And the reason why we do ordinary least squares instead of ordinary least absolute values is actually kind of an artificial one. When you take the mathematical solution, the analytical solution for this, it's actually a lot easier to do it with squares than it is to do it with absolute values. It's a lot easier to compute. And so back in the day, before we had really fast computers, squares, doing the analytical solution with the ordinary least squares is a lot faster and easier than doing it with absolute values, and that's why. These days, you could actually run regressions with absolute values as opposed to squares, and it would be totally fine, and computers can handle that, right? But because of that, we've built up a whole set of intuition around linear regressions that are using the minimization of the squared error term. oh, and I keep saying errors, and to formalize that, right, the error in this model is the difference, right, is that distance that I'm talking about. It's the difference between the point and your line, which is kind of your guess or your prediction, right? That's the black line. Okay, so you can do absolute value, but it's analytically difficult. Okay. So I can describe that line that I drew in an equation that might look something like this. So yi equals beta xi plus alpha plus epsilon I. Okay, there's a couple different things going on here. This is just the equation of a line, where you have, right, in algebra in high school we learn, oh, let's turn it off. Okay, in algebra in high school we learn that y equals mx plus b, right? M is the slope and b is the intercept, so it's the same thing here. Beta is the slope, alpha is the intercept, and so up here, slope equals alpha, slope equals beta, and intercept equals alpha. So the I is the ID of each point. This beta coefficient or slope, this is the alpha or intercept, and this is the unobserved error term. So I'm going to write out like a couple common forms of this that you might see, and then we'll talk about the differences between like this equation and other forms of this equation. Okay, so y equals beta x plus alpha, yi equals beta xi plus alpha plus epsilon I, which is what we saw, or what I wrote out here, and then you've got something like yi hat equals beta hat xi plus alpha. Okay, so these are all kind of describing kind of the same thing, but there's a little bit of nuance that's happening here. Okay. Y equals beta x plus alpha is just describing the relationship between your y and x, but it's actually maybe a little bit more accurate if you're drawing that line, is to write something like this. So the little hat, that caret symbol, is indicating that that is a prediction as opposed to a true value. Okay, and so in this plot, which things are true values and which components of this plot is a prediction?
Isn't so the data points are not a prediction, those are measurements.
Yes.
But the line is a prediction.
Yes, exactly. So when you're describing the line, really you're talking about like the hat part of it. And then these x's are your true y's, okay? So if this is I equals 1, I equals 2, I equals 3, I equals 4, and so on and so forth, right? The equation here is describing each individual point, right? And we can get to the point by drawing the line and then adding the error associated with that individual point. But if I'm only talking about the line, right, there is no error term here, right? Confusing to anyone? Yes.
So I was looking at your graph and they said the intercept is alpha, but wouldn't that then,
Oops. Yep.
so shouldn't alpha also have a caret on top because we're just assuming that's where.
Ah, yes, sorry. Good catch. That's correct. Like to keep you guys on your toes. Okay. Any other questions about this? Okay. So how do I go about figuring out what the correct slope and what the correct intercept would be for a set of data points? So generally speaking, there are two ways to do this. So numeric methods. So this might be something like gradient descent. And so this solves for beta iteratively by guessing and checking. But it guesses and checks in kind of a smart way, right? And so the idea is something like, I have a bunch of points in my plot, and then I'm gonna plop down a random line somewhere, and then I'm gonna look at it, and I'm gonna say, okay, can I do better? And then I'm gonna draw a new line and see if the total sum of squared error, right? So that's the squaring the error, adding it all up, that term, we're gonna call that the sum of the squared error. And we can see, okay, if I draw a different line, can I do better? And it's essentially this guessing and checking approach, but done in kind of this clever, smart way. And then you've got analytical methods. And so this is a solved optimization, essentially. So if you have taken a regression class before, maybe you'll recognize this equation, right? So it would be something like beta hat is equal to xtx inverse xty. So it turns out, so doing a regression is actually just an optimization problem, right? And so if you're familiar with optimization, you're doing something like, okay, minimize the sum of the error terms, which would be yi minus yi squared with respect to beta comma alpha, where y is equal to, beta x plus alpha. Okay, and so you know, this is a mathematical optimization and you can like solve it in some kind of optimization solver, but it turns out there is like a real analytical solution where I can mathematically figure out that actually the beta that you should have can be solved for exactly using this equation. Okay? So in this class, we are not really going to get into the theory, you know, and proofs and stuff like that behind this. So for folks who have taken regression classes, you probably have done stuff like derive this, right? We're not doing that in this class. I'm just going to kind of point out that, you know, this is the thing that's kind of happening behind the scenes, and you can trust that it's correct, right? So, you know, in R, when you do the LM function, which is how you do linear models for OLS, generally speaking, it's going to be doing this exact procedure, right? But what I will say is that it turns out that even though the analytical method seems like kind of the best way to do things, it's like the solved equation. It turns out that once you get to much larger data sets, and so we're talking about kind of more in what people might consider like machine learning territory, we've actually gone back to numeric methods to solve them. And the reason for that is actually right here. This -1, this is taking the inverse of a matrix. And it turns out that's actually very memory intensive. And so for the most part, for most linear regressions that you're going to be running, you're probably going to be doing this, but just know that actually at some point, the memory intensiveness of this process actually switches over to making this to be a little bit more efficient and actually a lot faster with really, really large data sets. Okay, so gradient descent actually, you know, made a comeback with linear regressions. And because that is like a guessing and checking iterative method, you're not actually gonna get like exactly the right solution, but it'll be close enough. Like you most of the time wouldn't be able to tell the difference between the answer generated from a numeric method versus an analytical method. Okay. Questions about that? Okay, so we are going to jump over to an example in R. Okay, let's see here. Oh, caps lock. Linear regression example. First line of code, I'm going to have something called, I'm going to assign to a variable I'm defining as x, and that's going to be r unif 20. So this is a function, and the input of the function is just a integer number. Well, okay, it's not actually an integer, but I'm putting 20, and essentially what this is asking or saying is please generate 20 random numbers between 0 and 1. So our unif stands for random uniform distribution, and it's sampling from a random uniform distribution with assumed parameters min equals to 0, max equals to 1. You can change that if you want, but for the purposes of this example, we're just doing our unif 20. And so if I run this and I take a look at x, you can see that I have generated 20 numbers randomly between 0 and 1. Okay? Next, we are going to generate an error term. And this is r norm 0.1. you can see that in the autocomplete, it is telling me what the inputs are. So I have n, mean, and standard deviation. So R norm, can anyone guess what R norm stands for? If R unif is R uniform, R norm is random normal. Okay, so we are drawing from a normal distribution, and I am setting the parameters. So the default parameters are 0 and 1. I'm going to change it a little bit. I'm going to say the mean is going to be still 0, but the standard deviation is going to be 0.1. Okay, and I draw from that 20 times, hit enter, and I can see that I have generated what I'm calling error. Okay. And y is x times 0.5 plus my error term. Okay, so if I plot that really quick, plot x equals x, y equals y. Do something like this. So, yeah, I didn't cover plotting in the tutorial. I'm using the base level plot, not ggplot that I described before. So don't worry too much about the specifics of the code. You can kind of just follow along when it comes to the plotting part of it. And that relationship looks something like this: my x's and my y's. You know, what's unique about what we're doing, or what I'm doing right now, is that actually ordinarily there's two things. The actual things that we would get from data is just my x's and my y's. So imagine I had like an Excel table, right, that had x as a column and y as a column, and then the data points corresponding to that. I am acting kind of as an omniscient entity here, in that I know what the error is, and I know this y is equal to x times 0.5 plus the error term. So that is what we call kind of the true relationship between my x's and y's. I have defined that. That is like ground truth. And normally you wouldn't have that information, right? We would only have where the x's are and where the y's and the corresponding y's are. So let's do something like this. Let's run the model. I'm gonna create an object called model.fit, and we are gonna use the function lm. So lm stands for linear model, and you are supposed to put in a formula here that describes your response variable and your explanatory variables and how you kind of want to set that up. And so on the left-hand side of the tilde, we have our response variable, and on the right-hand side, we have our explanatory variable. So we are regressing y on x, okay? And if I run that, and then we can do and actually let me do one more thing, just to kind of set this up a little bit better. I'm actually going to make this into a data frame so we can structurally see how it would be, how you typically would put in data into the ln function. Okay, so I'm setting up a data frame that looks something like this. And And so if I click on it, right, so this is my X's and Y's, just like data that might be set up in, you know, something like in Excel. And I can call that using the data option in LM. Okay. So this says the column called Y and the column called X, and we're getting those columns from this data frame called forModel.1. Okay, so I'm going to run these two. And I can do summary of model.fit. So model.fit is an object that is storing all of the outputs of this function. And one of the ways that you can call it is using this summary function, and you will see an output that looks something like this. So it tells you here what the formula for that is. It tells you something about residuals, and we're going to talk about what this means a little bit later. And then the coefficient estimates. Okay, and so here it is saying the estimate of the intercept is -0.047, and the estimate of the slope for x is 0.576. All right, what is the true known slope of x? And what is the true known intercept of x? Anyone? 0.5 and... So this is the predicted, but there's a true relationship between x and y that normally you wouldn't know, but in this case we actually do know. 0.5, right? And so like I said earlier, that is this thing. I literally defined y to be that, okay? And so what does that mean here? So we are slightly off somehow, right? And so this prediction actually is not a exact prediction. And in fact, this regression model tells us that via these standard errors, okay? And so before we jump into that, let's talk about kind of theoretically what a standard error is. Okay, 1 second. We're going to jump back over. Okay, actually before that, any questions about this? So, as it turns out, as I was saying, kind of the estimate of our slope is a prediction, but the prediction statistically comes with some uncertainty about essentially how accurate that is. So let me give kind of an example of what this would look like. So I'm going to draw two plots kind of side by side here. Okay, and do something like this. And you might have a line that looks like this. this one might have a line like this. Okay, so what I attempted to do, so the cluster points is kind of exactly the same between this plot and this plot, but on the right-hand side, they're just kind of like farther out, okay? And so the estimate of the line actually ends up being pretty much in exactly the same place, okay? I want you guys to think about what it would mean for me to, let's say, remove a certain point, right? So if I were to remove this point and this point. So essentially, if the point is, if all the points are like really close to the line and I were to take one away, that line wouldn't fluctuate very much, right? It would stay within that same slope. But if the points are all kind of really far from each other and then you took one out, you might imagine that that line wiggles a little bit more, right? The points end up having like a greater influence on how we end up drawing the slope, right? So the idea here, if a point is taken away, which beta is likely to change more. Okay, so I'm going to give the equation for how we would go about calculating the standard error, which is, right, the measurements of what I'm kind of qualitatively trying to talk about here. So this isn't something that you need to memorize, and this isn't something we're like deriving or anything. This is kind of just for your reference. But it's more important that you kind of understand what a standard error is representing. Okay, so why am I blanking? The sigma, right? Sigma of beta is equal to the square root sum yi minus yi hat squared n minus 2 over xi minus x squared. Okay, so that's the equation. Like, if you really need to know it, you can always look it up. You're not really ever going to be, right? And other than some econometrics class, you're never going to be calculating these by hand. But more important is kind of the intuition behind it, as I was saying, right? So standard deviation is kind of related, but not the same thing. And so just to clarify the difference, so this is how does the data deviate from the mean? Whereas the standard error is how precise is our estimate of the mean. Okay. Any questions about this concept? Yes.
Is it a basically one-to-one direct relationship between the two, standard deviation, standard error? You want to have one go up and the other go down under any circumstance?
I can't think of any.
Okay.
Yeah, it should be, but I'm not gonna say that answer is like gospel, because I don't know if there's like some kind of weird exception to that. Yeah, I mean, generally you would think so, right? So, the more, it is actually exactly this thing, right? Like, the more dispersed the data is, our standard errors are actually increasing. And in fact, let's show that, right? So we can do that explicitly. So, let's do something like this. Y2 is x times 0.5 plus error times 2. Okay, so these points are like literally in the exact same place, except that they're like pushed off slightly farther. So in exactly the same way that I was kind of describing before. And in fact, I can plot this, and so I'm gonna hit enter, and I think we should see this same shape, but the points are like spread out farther. Obviously I have to run Y2 first. Right, and so the line going through them, is the slope gonna be the same or not?
Be the same.
It would be the same, right? In fact, we know that, right? Because the slope is still 0.5. Like I set the slope to be 0.5, and so we should expect the slope to still be 0.5. But the literal error we know is bigger. Okay, and so let's look at that. Example model 2. Oh, let's make a new data frame just to be consistent. So for model dot 2, data frame x equals x, y equals y2. This is going to be lm y on x, data equals for model 2. And we'll run this. Summary.
Just like your, yeah.
Oh, yes. For model dot 2. Okay. Okay, so here our estimate is 0.57644. Standard error is about 0.1. Okay? And here, the estimate is different, and the standard error is about 0.2. So it's larger. Yeah, so it just so happens whatever random points that we ended up drawing from this are seemingly influencing a little bit more, but in fact, let me do something. Let me change this from 200 to 1,000, and let's run this whole thing again. Okay, and now you can see with 1,000 points, our slope is a lot closer, right? It was 0.7 off before, and now it's 0.0053 off now. And our standard error is 0.01. And what about for the other one? Again, coefficient ends up getting closer to the truth. And the standard error is 0.02. It's twice as large as the other one. Okay, so if the data is dispersed more, I'm going to say generally our standard errors are going to be larger. Okay. Yeah. So what is the standard error actually kind of representing? In this case, let me jump back here. So we have our regression, and we have the line going through all of these points, and the idea is something like, okay, like that's one estimate, that's like our average estimate, but like maybe sometimes like the line could be something like this, it could be something like this, it could be some percent of the time it might look something like this, right? And so there is actually a distribution of slopes, okay? And so if this is the average beta value, when we're doing these guesses, we're including the uncertainty about that average beta value. And the uncertainty is actually built in a normal distribution, okay? And so this is our average beta value, and the parameters of this particular normal distribution are defined by the standard error. So this is our sigma for beta, and that says that some percentage of the time the slope is, you know, within a certain bounds, right? And so similar to like standard deviation, one standard error away from that coefficient means that, what is it, 68.5% of slopes are going to be, of the guesses of our slopes are going to be, you know, from that plus or minus that standard error value. Yes, so what did we have? We had beta equals 0.5, and we had sigma is equal to, let's say, 0.1. That was like in our original one, in the one where we had 20 draws. So this means that I interpret this as 68% of the time beta is between 0.4 and 0.4 to 0.6. 95% of the time beta is between 0.3 to 0.7, and 99, right? 99.7% of the time beta is between 0.2 and 0.8. Is everyone kind of following along here? Yes, okay. So I know this is kind of review for some of you guys, and we really want to make sure our intuition about what the standard error means is correct, and that, and I'm going to talk about some, I think, extensions of how people interpret standard errors to mean a lot more than they actually do, right? So who's heard of statistical significance? Yes. Are you the only person? Anyone else heard of statistical significance? Yes, a couple people. Okay, do you want to tell me what statistical significance means?
It's a prediction or probability that you're within a certain error from that. Like,
Yeah.
estimate.
Okay, so I think you're like kind of there, but I want us to be like rock solid on this intuition. So okay, let me jump back here. We have a bunch of different possible slopes, right? These are probabilistic. So in some percentage of the time, there exists some slope that could be an estimate of the fit, okay? So what would it mean if I drew a slope that looked perfectly horizontally flat, like that? What is the like qualitative meaning of a horizontally flat slope? Yeah, so don't think about the mathematical interpretation. Like think about what is the relationship between x and y if your fit is a flat line. What was that? Yes, constant. So in other words, y, the variation in y is not explained by changes in x, right? So any value that I pick, y will be the same, right? Anywhere I go along this line, y doesn't change. So basically, you know, people gravitate to this idea of statistical significance because you're basically saying that if it's not statistically significant, the argument is that changes in x don't have any effect on the y outcome. Okay, so what does that mean here? Okay. So let's say beta is equal to 0.2 instead of 0.5, and our sigma is equal to 0.1 still. Then all of this stuff is the same, but that would be going, beta is between 0.1 to 0.3, and then it would be 0 to 0.4, and then negative 0.1 to 0.5. So the idea is, okay, like some percentage of the time you hit 0, okay? And that's what we're looking for when we say something about statistical significance. It's just saying, you know, what percentage of the time do we think there's like no effect, or that we couldn't tell the difference between a positive effect and a negative effect. And so in this particular case, you know, we would say there's this threshold where like 5% of the time you are gonna hit this at a 0 threshold, and so we would say this is like statistically significant up to that like 5% threshold. Okay? Questions about that? Yes?
Repeat that last part, please.
Yeah, so if you've built the intuition correctly here, all we're saying is we're doing the same thing, and we're essentially have this like special flag or marker for when it hits 0, right? Because at that point we're saying, oh, it doesn't really have an effect. So statistical significance is saying, you know, at a certain threshold, if it's at 10% or 5% or 1%, we are arguing that actually it does or does not have an effect, right? Depending on where that threshold is. Okay, so let me kind of back up here and say that you know, it's very common for me to see people presenting work and models, and they're like, hey, look, you know, I've got great statistical significance here, and that means that the model is great, and we're doing all these like fabulous things, and like, yay, like it's a great paper because we found statistical significance, right? Doesn't say anything about how good a model is, right? It's only saying something about whether or not the slope isn't 0. That's all, okay? And so we need to be kind of careful about extending results to mean more than they are. We're gonna look at a whole bunch of different ways of doing like real model diagnostics, and not just this thing about statistical significance and how, you know, it is one measure of something in the model, and it might be something useful and something that you're looking for, right? But in and of itself doesn't tell you anything about how good the model is. And in fact, I could come up with models that have, you know, great statistical significance, but if I built the model wrong, you know, those things, again, don't really mean anything, okay? Okay. So we're doing a little bit of like kind of debunking here. And the other one that I want to talk about that people often kind of refer to is the R squared. So R squared, yeah, we're looking at all the different components of that summary table that we saw. We're going to break those down kind of one at a time. So one of the other ones that was in there is called the coefficient of determination. And this is how much variation is captured by the model. Okay, so once again, I'm going to provide you guys with the equation. This is just for reference. R squared is equal to 1 minus SS res over SS total. So this is the residual sum of squares, which we'll talk about a little bit more later. And the bottom is the sum of squares total. So 1 minus the sum of yi minus yi hat squared divided by the sum of yi minus y bar squared. Okay, so that's the equation. So what does that actually mean? Okay, so to kind of build the intuition on this, I'm going to draw two plots again, kind of side by side. Okay, I'm going to do something like this with the exact same points. The plot on the left is this denominator term. So this measures the error if my line were just defined as the average value of y. Okay, so I just take this, I average it and draw a straight line, and then I measure the errors. Okay. And that is compared to what we've been talking about, the sum of the squared error terms like this. So this is the sort of best fit line. And the idea here, what the R squared is asking is it is saying, hey, like how much better is our thing compared to a naive just taking the average of all the y's, okay? And it looks at the ratio of those and it's 1 minus that. And so the larger your R squared is, the more it explains, the more it reduces, right, these errors. And so the more it reduces, it captures the variation of the model, right? And so the idea, how much variation does it capture compared to the average? Okay? Questions about this? So kind of likewise to standard errors, R squared is the other term that I like very commonly hear as the kind of end all be all for kind of a how good a model is. You say, oh, my model has a really high R squared, therefore it's amazing. Or my model has like a really low R squared and therefore it's really crappy, right? So no, that's not what any of this means, right? The R squared just measures the variation that's being captured by the x's. And you can have models that have very poor R squared, but that do a really good job at understanding relationships between x's and y's. It's just that there may be other things that are leading to noise in the model or leading to variation in the model that maybe you don't care as much about, right? And so don't focus solely on R squared as a metric for how good a model is, right? We really want to build the intuition to have like a good grasp of what an actual R squared and what an actual standard error is referring to, and what that means in terms of the quality of the model, right? These things are helping to explain just like one little bit of that. Okay. Questions? All right, so let's go back here, and we're gonna look at some more stuff here. Okay, let me actually go back to 20 here. Run all this stuff again. Okay. And you can see, oop. Hang on. There we go. So I reran the code, I dropped it back down to 20 draws out of the random distribution. So we've talked about what the estimate is referring to, that's the coefficient value for our slope and our intercept. And we've talked about the standard error. Okay, the t, for those who don't know, so the t value and this probability, so what are these guys talking about? So this portion of the table is in reference to the statistical significance stuff. And so the t values here are how many standard errors away from 0 am I? So if you do 0.6 and this is 0.095 or about 0.1, right, then you are about 6 standard errors away from 0. That's what a t-value is. Same here, t-value here. The estimate is about negative 0.058. The standard error is about 0.05. So you're close to about 1 t-value away, 1 standard error away from 0. And so this tells you then the corresponding probability. There's like a lookup table that you can go to that tells you what's the probability then that that term, that the coefficient value is reaches 0, right, in that uncertainty thing, in that uncertainty distribution. And so for our intercept, 30% of the time it's 0. For our slope for our x, 0.00006 times it's going to be it'll be 0. So very small probability, right? And then we can look at our R squared value, and that's that's gonna be 0.68. Don't worry about the adjusted R squared, we're gonna get to that later on in this class. Okay, and so the R squared value tells us the reference for R squared is actually typically between 0 and 1, so the closer you are to 0, the less variation you're capturing. The closer you are to 1, the more variation that you're capturing. Yeah.
I just want to ask, so we look at the t-value for x, and because it's 6 standard errors, that means 99.99.
That's this probability. So 1 minus this would be 0.9999994% of the time, or 99.9994% of the time would be larger than 0. So it's very unlikely that the slope is 0 essentially. Okay. One of the things to note, okay. Let's do x3.
Do these values you're talking about, like t-value, do they change if we're not running like a linear regression? If we're assuming non-linear behavior?
Yeah, so if you drew a curve that's not straight, that's kind of like this, right? I could still come up with some kind of, well, okay. The t-values, I mean, this part of it is not really any different for any other type of line, but the intuition behind what it's referring to in a parameter estimate is not the same, because in this case, it's kind of easy to think of this as a slope, okay? But when we're getting into nonlinear territory, oftentimes the parameters are like not an immediately intuitive like thing. So for example, if I were to do something like this. So instead of y equals beta x, where this is just the slope, imagine if you had a line that was defined as x, or y is equal to beta 1x plus beta 2x squared plus beta 3x cubed. So these are parameters that help you define what the line looks like, right? And so if I had one beta, my line might look like this. If I had a different beta, my line might look, maybe the line looks like this, right? And that depends on the values of the betas here, much in the same way that the analogy would be, instead of this slope, it might be this slope or this slope, right? And so there is a average estimate of what that parameter would be, and that still would follow, a lot of the times would still follow a normal distribution, not always. And in that case, if the error about that parameter, is describing like the standard errors like in a linear regression, then yes, the t-values and stuff like that would be the same. It's just that the beta isn't really strictly a slope anymore. Does that make sense? Yeah. And so the t-value stuff describing a normal distribution about the mean value of a parameter doesn't go away when you're not doing a linear model. It can if you assume that the errors are not distributed normally. And there are some cases in which that happens. And in fact, we'll even talk about some special cases like that later. Okay, any other questions? Okay, so I'm gonna do something like this. We're gonna do a million draws. Instead here. And I can see this isn't gonna break my computer, is it? Okay, oops. Maybe it was a bad idea to plot this, but we'll see. So we're just doing the same thing as we did before, except this time we're gonna have a lot more draws. Like a lot more, right? Yeah, okay, so we have just like a ginormous cluster of points in there. It's like completely filling up all that space, and let's see what happens. Oh, oops, that's not what I meant to do. We need to do example dot model 3 y3. So we can just do y on x. Data equals 4 model dot 3, and we'll look at the outputs of this. Okay, so our estimate is really close to 0.5. It's not like, so what's the ground truth one? It's exactly 0.5, right? And so we're still off by a little bit, but then, you still have a little bit of error. And so we're actually right in that margin, right, of what would be 0.5. The standard error is way smaller, and so what is that telling us? What's the intuition? Come on. Anybody?
With more data points, the error becomes more precise. More sampling.
Yeah, okay, let's be precise here. So with more data points, our estimate of the coefficient becomes more precise, and that's related to the smaller sort of standard error. And in fact, we see that the probability here that it's 0 is much smaller, although, okay, maybe we care a little bit less about that, because we know that it's not 0, right? We want to know how close this is to the true value, and it does appear to be a lot closer to that true value. What do we notice about the R squared value? the summary. Okay, actually wait, let me step back for a second. Here are the results for model 3 and summary. Oh, what did I didn't call it example model 1, did I? I called it model.fit. Okay. Summary model.fit. Okay, so everyone take a close look at the one with the 20 draws, right? Look at the coefficient values and the standard error values and our R-squared values. 0.6866. And in this case, with 1,000,000 points, here's our estimate, here's our standard error, and our R-squared is 0.6764. Okay, which one has the higher R-squared model? The first model or the third model? The first one, yeah, right? So this is 0.6764, 0.6866, right? And so, does that mean that the third model is better? Or sorry, the first model is better than the third one? Because the R-squared is higher? What do you guys think? Maybe, maybe not. Okay, so hopefully you guys can see, right, that the third model that had 1,000,000 data points, it was a lot more accurate in terms of the coefficient values. It's like way closer, right, to what we know is the truth, so we can objectively measure which one is better. And yet, the model metric that a lot of people go by, like an R-squared value, they're like really close. And in fact, in this particular random set of numbers, the first model ends up being having a higher R-squared values, right? And so the R-squared is not everything. Okay. Questions about this? Okay. We are going to look at one last thing. So no need to follow along here in terms of typing. I'm going to read in a data set which you guys don't have access to, so you can't even follow along even if you wanted to. So this is a CSV called the Anscombe Quartet. Who's heard of the Anscombe Quartet? Anybody? Okay, great. We're gonna read in a little set of data, and there are 4 pairs of X's and Y's in this data set. And so what I would like to do is actually to run these models, and I would like for you guys to interpret them, okay? So read.csv, so we haven't really covered this in class, but read.csv is a function that lets you read in comma separated value data sets, okay? And so there's this little thing that I'm reading in, and I'm assigning that to the variable A. Okay, and I'm just gonna run these 4 models, and we're gonna look at a summary. Okay, I know we're very shy today, but I would like one more volunteer. Come on, just raise your hand, don't worry, you can't get anything wrong, you're not being graded here. Alright, I'm gonna pick someone then. Ray. No, you can stay there.
Oh.
Don't worry. I'm not gonna ask you to get out of your seat or anything. I've just run the summary for Model 1. Can you please interpret this model output? Give me your thoughts about what's going on here. Okay, tell us about, simple, let's start here. What are these values?
The coefficient of x1 is 0.5,
Great.
which is pretty similar with the one that we.
Oh yeah, don't forget about the previous examples. There's no relation actually. Just coincidence.
Mhm.
Okay, so it has a slope of 0.5, and this value is what?
Intercept.
Intercept, okay? So everyone kind of visualize, we have a slope of 0.5, intercept of 3. Okay, so look at these values here and what do you think?
The standard error, this predicted value from the mean value is 0.1 for x1,
Okay, great.
and
So it's, what would you say about this part here? So this is the percentage of time that it reaches 0, right? And so it's like statistically significant. This is a way of interpreting it to the 1% level. Okay. What about the R squared here?
66%.
Yeah? Okay, so, alright. So, aside from the interpretation, so you're looking at this like model output, what do you think? Thumbs up? Thumbs down? Is it a good model? Is it a bad model? What do you think? Okay.
Well, in general, yeah, it looks okay, but then I might try to find better fit model.
Okay, so you're like actually not all that satisfied. You think it's a decent model, but you're like, I can do better.
Yeah.
Okay, great, great. Okay, another volunteer before your voluntold. Okay, you are gonna help me interpret the next model. Okay, so we just looked at summary model 1, and now we're gonna look at summary model 2. Okay, you ready? Enter. Okay, this is a totally different data set. Okay. Tell me about this model.
It has similar values to Model 1.
Okay. Yeah.
But
So like 0.5
Yeah.
on the coefficient, for the slope, 3 on the intercept. My R squared 0.66, pretty much very close, right?
yeah, and also the statistical significance is pretty similar to the last one.
Yep, okay, so these are also close, and so your probability values are close, great. So what do you think? Is this a good model, not a good model? You agree with Ray? It's okay, but I could do better.
Yeah, I have seen better.
Okay, great. And when you say you've seen better, it's because like you've seen things that are more significant, you've seen things with higher R squared values.
Both.
Both. Okay, great. Okay, great. Can I get John? You want to tell me about Model 3?
I will say that my vision is really bad.
Oh, okay.
But yeah, I mean, I can see the 0.49 values.
Okay.
So practically, it's saying there's like the slope would be flatter than the previous model. So there's since that. Doesn't really seem like there's too much variation from like.
Yeah, okay. So we're saying that Model 3 looks a lot like Model 2, which kind of looks a lot like Model 1. And okay, do you think this model is good?
I mean,
Do you think this model is better than model 1 or 2? Or which of the three, and anyone can feel free to chime in here. If anyone thinks that a particular model is like better, feel free to chime in. Yeah?
In any specific way?
Yeah, we're just saying like how good a model is, right?
I just wanna ask, these are all using the same data sets?
No, there are
Okay.
4 different data
Okay.
sets.
Alright.
Yeah. And, okay, well, so I guess you guys can probably guess what's gonna happen here. Summary model 4, oh hey look, it's about 0.5, it's about 3 for the intercept, r squared 66, or 0.66, and you know, 0.2% and 2% significant here. Great. So, and you guys all think that these are like, these models are kind of decent, not too bad, decent significance, okay r squared, right? Everyone's kind of like middling happy, yeah.
Am I correct, in order to determine whether these are good models or not, it's contingent and we have to look at the data. Because there may be things such as lurking variables that can influence each data set and such.
Yes, good advice. Okay, we want to look at the data. So this is the Anscombe quartet. So these are, here, let me pop this out. Which button is it again? Zoom? Yeah, here we go. That's even better. Okay. This is an artificially constructed data set called the Anscombe quartet, right? And if you thought that the strength of the models rely only on the standard errors and the r squared, right? Look at the data, and you should see, right, that the intuition is not correct, right? Our ability to understand how good a model is, right, is different from what these values are telling us, right? The values mean something, right, and they're not different. Like statistical significance doesn't mean something different for this plot versus that plot. R squared doesn't mean something different, you know, for plot 4 versus plot 1, right? But our ability to say how good a regression model is should be extending beyond these common metrics, which people usually talk about when they're talking about the goodness of a model, okay? So in this case, all of these models have essentially identical coefficient values, identical standard error values, identical r squared values. And if that was the basis on which we are judging our models, then we would say that they're about the same, when they are clearly not, okay? So, as we proceed through the class, we are going to be talking about other ways and other means and metrics of measuring what we call kind of the goodness of a model. We're not going to dismiss things like standard error and statistical significance and r squared. Those are pieces of like a larger toolbox that will help us to understand and interpret kind of our model fits, okay? But there's going to be a lot of other things that we want to look to rather than just like having those as the central values on which we're doing a lot of this analysis. Okay? Any questions about this? Cool. Okay. And so I will post. I'll post that data set related to the Anscombe quartet so that you guys will be able to run this code. This again will be all available on Canvas. Yeah, today our first homework set is posted. So you guys should all be able to access that homework, and it will be due next Wednesday, so you guys have a week and a couple of days. Yeah, so make sure to start early, especially if you are kind of learning R simultaneously. It might take a little bit more time. You know, you gotta build that practice to get good at it. Otherwise, my office hours are on Thursday if you need help with the homework or if you want to go over any of the material that we've thus far covered. And Yanning, her office hours are tomorrow, Tuesdays in the afternoon. Okay, and so that's it for today.